In 1887, Heinrich Hertz discovers something. He discovers that when light, or EMR, strikes a metal, or other materials as well, but especially metals, electrons will be ejected sometimes. Not always, sometimes. He tries to explain this. His explanation goes like this. When EMR, or light, we use those terms interchangeably, strikes the metal and electrons are not ejected, we need more energy. We get that from having more light, brighter light, more intense light, or shine the light on the metal for a longer period of time. But that didn't work. 18 years of observations contradicted that explanation. If there was a certain type of EMR that was not causing electrons to be ejected, then that type of EMR would never cause electrons to be ejected, regardless of how much you had. In our little demonstration that we did 5 minutes ago, 1 bit of light didn't cause an electron. 100 bits of light wouldn't cause an electron to be ejected. The observation showed that it wasn't how much light you had, rather it was the frequency. But nobody could explain that till Einstein. Einstein comes along and says, light's a particle called a photon. And the energy of that photon is related to the frequency of the photon. So Einstein said, if you want more energy to cause an electron to be ejected, you don't need more light. If you want more energy, you want more frequency. If visible light doesn't cause this to happen, then don't get more visible light, don't get brighter light, don't get more flashlights. Get a different kind of light. Get ultraviolet, get X-rays, get gamma rays. This doesn't necessarily seem so revolutionary to us, but it is. Because up until this point, 1905, it was done, it was settled. EMR is a wave. But now we're saying the only way to explain the photoelectric effect, the observations that were made thousands of times, is that light is a particle. It's still a wave, but now it's a particle too. A particle with an energy equal to h times f. Let's define a term. It's called the threshold frequency. What does the word threshold mean to you? Somebody in the last class mentioned pain threshold. That was a great example, pain threshold. What is your pain threshold? Some people have a higher pain threshold than others. What does that mean? Your tolerance for pain? Yeah, sorry, go ahead. Yeah, some people can tolerate more pain than others. Some people, when they get a bump, doesn't really hurt. It's below their threshold of pain. Some people, when they get a little bump, it hurts lots. They complain lots about it. It's above their threshold of pain. So the threshold of pain would be that minimum amount of pain that you'd feel. Yeah? Yeah, the threshold frequency given by the symbol F0, or in most parts of the world other than North America, maybe we call it F0. We call it F0, or the threshold frequency, is the minimum EMR frequency necessary to eject an electron. We've already established that it's not the intensity, right? Einstein said it's not the intensity at all, the brightness of light at all. It's the type you have, the frequency you have. So now we're saying that if you're below a certain frequency, nothing happens. No electrons are ejected. F0, the threshold frequency, is the minimum EMR frequency necessary to eject an electron. Now, there is another term that kind of goes along with that, and that would be the threshold wavelength. But we're not going to call that F0. We're going to call that lambda max. It is the maximum EMR wavelength necessary to eject an electron. You can imagine here, since frequency and wavelength are inversely related to one another, that a minimum frequency would correspond to a maximum wavelength. In our demonstration, the pieces of paper were below the minimum frequency. They were above the maximum wavelength. If you're below the minimum frequency, above the maximum wavelength, nothing's going to happen, ever. Doesn't matter how much of it you have. One paper didn't cause an electron to be ejected. 12 papers didn't cause an electron to be ejected. 1,000 wouldn't either. Here's another term. It's called the work function. The work function is given by the symbol W. The work function is the minimum energy necessary. Of course, this frequency is related to energy. If you have a minimum frequency, you're going to have a minimum energy. Any photon that has more than that energy causes an electron to be ejected. Anything that has less causes nothing. The equation for energy is HF or HC over lambda. That entire thing, by the way, is on our data sheet. The equation for work function, if energy is HF, then minimum energy would be H times minimum frequency. But if it's HC over lambda, then it would be, the minimum would be HC over lambda, what is it? Max. Now I want to box off this part of it because that's the part that appears on my data sheet. HC over lambda max doesn't appear on the data sheet, but it's not that hard to come up with on your own, right? Given the other equation up here that does appear on the data sheet. So there is a minimum frequency. It's called the threshold frequency. When we're below the minimum frequency, photons that have a frequency lower than that minimum frequency, that threshold frequency, cause nothing. If we are, look, if our frequency is below the threshold frequency, nothing happens. Photons above the threshold frequency, right here, photons that have a frequency that's greater than F0 will cause electrons to be ejected in a 1-to-1 ratio. So in other words, you're below the threshold frequency, one photon causes nothing, 1,000 photons causes nothing. You're above the threshold frequency, one photon causes one electron, 1,000 photons causes 1,000 electrons. One more little bit here, guys. When electrons are ejected, it says in the next paragraph, higher frequency makes them more energetic. Like, think about what that means. Electrons are ejected. Our frequency now is not just above the threshold frequency, it's way above the threshold frequency. So in blue there, we were below the threshold frequency, nothing happened. In green, we were above the threshold frequency, one photon caused one electron, 20 photons caused 20 electrons. Now we're way above the threshold frequency. Well, guess what? That's still a 1-to-1 ratio, but it's more energetic. What does that mean? You're way above the threshold frequency. One photon will still cause one electron to be ejected. 1,000 photons will still cause 1,000 electrons. But those electrons will all be more energetic than they would have otherwise been. Which makes sense, right? You have higher frequency, you have more energy. More energy is going to cause the electrons to be more energetic. And what do we mean down here? More photons causes more electrons. That goes back to the 1-to-1 ratio, right? One photon below, nothing happens. But one photon above, one electron ejected. 20 photons cause 20 electrons. More photons causes more electrons. And more photons translates to, we could say, brighter light, more intense, Like instead of having a dim flashlight, you got a bright flashlight. You got, instead of having one flashlight, you have two flashlights. Instead of having a flashlight for a little bit of time, you have a flashlight shining on it for a longer time. That does nothing if you're below the threshold frequency, but if you're above the threshold frequency, it gives you more photons, which gives you more electrons, but only if you're above the threshold frequency.